This video is in response to a question asked by Tricky 3003, and he asks if we have an equation where we're trying to explain wage with a y-intercept, a female dummy variable, a married dummy variable, and a height continuous variable, why would you create a new interaction term in this regression like, and Tricky 3003 says someone supposedly creates a variable female times married. He says he's not sure what this extra interaction term adds to the analysis and how would we interpret it. And my first instinct was to tell Tricky to go and watch some of my previous videos, but after I thought about it for a second, I realized that I don't have a video where I interact two dummy variables. So let's talk about that briefly. Before we look at this specific example, let me give you in general how you can think about what this term would mean and what it would add to your analysis. Imagine putting your data set together, what it would look like. And let's just focus on these dummy variables. We're going to have in our data, for example, and you don't have to do it exactly this way. Some programs will do this for you, but think about what your data would look like. We're going to have a dummy variable for female. We're going to have a dummy variable for married. And with the interaction term, we're going to have female times married. And then we're going to have this height variable here. Now, when you're putting your data together, think about some specific people. We might have someone in our data set who is a female, that's a 1, who is single, so 0, not married. And so what's female times married going to be? 1 times 0 is 0. Now let's look at another person in our data set. They are female, and they are married. What's the value of female times married? 1 times 1 is 1. And let's just put another couple of people in here. Let's see, we have a male, and he's single, and 0 times 0 is 0, female times married. And lastly, we have another guy who comes into our data set. He's male, he is married, and so what's 0 times 1? Female times married, it's 0. And so keep in mind that an interaction variable, when you write it times in your equation like this, literally that is what you're doing. You're multiplying the values together. So this female times married variable is going to take the value 1 only for what kind of person? Well, it's going to take the value 1 for someone who's female and married. And so that's exactly what that interaction variable is going to pick up. It's going to tell you the difference between someone who is female and married from the other types of people in your data set. And so if you have someone who's female and single, that person might be different from someone who is female and married. And that's really what this dummy variable is going to pick up for us. So let's go to a graph and look at what might happen. Okay, let's start by assuming that we did include the dummy variable interaction term, the female times married, and let's see what each of these dummy variables and slopes and interaction terms are going to tell us about these relationships. And then let's suppose we left it out and imagine what might happen if we do that. And so here are our estimated coefficients when we include a y-intercept. Let's suppose that's 4. A dummy variable for female. Let's suppose the estimated coefficient for that dummy variable is 2. And a married dummy variable, our estimated coefficient is 3. Our height slope is 1. And our interaction coefficient is -6. Let me slide that over there just a little bit so you can see that a little better. So what do all these things mean? Well, all we have to do is start graphing lines to see what happens. Now let's start by assuming that all these dummy variables are 0. What is the equation of that line going to be? Well, the y-intercept will still be 4. The b1, since we're talking about all the dummy variables being 0, we're talking about a male, and so this is going to be 0. So we're just going to leave that out of our equation of a line. This person's not married, so that's going to be 0. And height will have a slope of 1. And if this dummy variable is 0, that means the person is not male or not married, right? We don't know which, but we already said so back here, that all the dummy variables are 0. So what we're going to be doing here is making an equation like this, where wage is going to be equal to 4 plus, okay, this is 0, so we leave it out. Married is 0, so we leave it out. So it's going to be plus 1 times height, and the other dummy variable is 0 as well. So we just have this very simple equation, and I want you to think about who this is that we are talking about right here. Well, this is 0, they're not male, and they're not married. So we're talking about a single male observation here. Now let's graph that line and just see what it looks like. And so I've already drawn some lines over here that I can just drag over and plop down. So this green line is for males who are single. And the y-intercept is 4 and the slope is 1. For each additional inch, the wage goes up by 1 unit or whatever here. And so the green line is a relationship between height and wage for single males. Now, let's assume that we have a female. Single female. What is this equation going to look like? Well, let's see. Let's just start off with wage is going to be equal to 4 plus 1 times height again, plus, and then we're going to have to include this term right here in this equation, b1 times female, and b1, our estimate is 2, so plus 2 times female. Dummy variables are either 0 or 1, and so we're saying this one is 1, right, since it's a female. And yeah, so 2 times 1. And not married, so that term's going to be 0 times the married estimate. And since the person is not married, then this b4 is also going to be 0. So we're just left with this equation, 4 plus 1 times height plus 2. Or we can rewrite that a little more simply as just add the 2 to the y-intercept. Wage equals 6 plus 1 times height. So this is going to be for single females. Let's graph this line so we can see what it's going to look like. So we, instead of the y-intercept being 4 like it is for males, the y-intercept is going to be 6 for females. So this blue line is the single female relationship between height and wage. Now, what's another case that we had when we were looking at making our data set? Let's see. Well, we had single males. We just did single females. That would be this row. Let's do a married male. Let's do a married male next. Okay. Married male. Let's type this equation in here. We're going to have their wage is equal to 4 plus 1 times height plus they're not female. It's a married male, so this b1 times female term will drop out. b2 times married we have to put in. So b2, our estimate is 3 for our coefficient. 3 times 1. Since this is a married male, 1 will be the value for the married dummy variable. But since they're not female, this last term will drop out. So we have wage is equal to 4 plus 1 times height plus 3. Well, we can write that more simply. Just add the 3 and the 4 together, collecting terms here. Wage equals 7 plus 1 times height. So we have another relationship here for single, oh sorry, this is for married males. So let's graph that line. The y-intercept is now 7. The slope is still 1. So we get something that looks like this red line for the married males. So what we're seeing is that just by assumption of these simple dots that I drew on the graph here, that the single males have the green relationship, the single females have the blue relationship, the married males have the red relationship. Now guess what's going to happen for this next set of people we have. The only people we have not addressed so far are the people who are female and married, because we haven't brought in this interaction variable yet. So that's what we're going to do right now. What if we had a married female in our data set? Well, their relationship would be wage equals 4 plus 1 times height, and plus the estimate for B1 is 2, so this is a female, so we have to add that in. 2 times female is 1, plus they're also married. B2 is 3, that's our estimate, times this person is married, so plus 3 times 1, plus, since this person is height, the dummy variable is 1. Oh, sorry, not height, sorry, not a dummy variable. Since this person is female and also married, the female dummy variable is 1, and the married variable is also 1. The interaction is 1, so we have to add in B4, which is minus 6. So plus minus 6 times 1, since that interaction dummy variable's value will be 1. Now let's look at what's going on here with an orange line before we collect all these together. Remember that a simple dummy variable like this, like all these, female, married, and female times married, we call intercept dummies. Because all that happens with these dummy variables is that it shifts the y-intercept up or down. So let's take this orange line over here and let's start off by stacking it on top of the green line for single males. We're not talking about a single male. This person is a female. So by being a female, that shifts the line up to the blue line, remember, for single females. But they're not just a single female, they're also married. What's the slope coefficient for married? Well, it's 3. And so because this person's female, we add in 2 to this y-intercept. Because they're married, we add in another 3, bringing them up about here, right? But that's not right. That's not what our data says. Married females aren't just people who happen to be female and also happen to be married. Those two things interact together. Married females have a specific difference. This married female coefficient of minus 6 says, yeah, according to the math, we're going to add in the 2 because they're female. We're going to add in the 3 because they're married, but then we're going to subtract 6 because they're both. And these dots that the orange line are going through might be the married females in the sample. So what this interaction, of the 2 dummy variables is doing is allowing us to estimate a separate relationship for single males, the green, single females, the blue, married males, the red, and married females, the orange. It is, however, assuming that the slope is the same for all four types of people: single males, single females, and married females. We haven't done any interactions on the slopes, but we could. We could. I'm not going to go through that, but and we could allow the slopes to be different for all four groups if we wanted to. But here, with this interaction of the two dummies, you're allowing a different slope for people who are both female and married. What would we learn from this exercise if these are the four lines that we got from these dummy variables? Well, we would learn from the green line that single males don't earn a whole lot of money, right? But when males get married, they go from the green to the red line. After males get married, maybe they're more responsible, they have to earn money to pay off the bills, and so they get a different job, and they're earning more money. In this case, the y-intercept, at least, we'd say ceteris paribus, for any given height, a male will earn 4 more. No, wait. Oh, 3 more, because the y-intercept goes from 4 to 7. Yeah. And that's what that estimate of 3 for married means. That ceteris paribus, when a male gets married, their income goes up by 3, from the green to the red. Now, also we learned that females, ceteris paribus, for the same height, will earn 2 more, because the y-intercept is 2 higher. That's what this 2 estimate for females means. If you look at a male and a female that are the same height, let me draw a little line here so we can focus in on some people that are like this. Let me color that yellow. So people who are 3, and how we're measuring height here might be how many inches above 5.5 feet are you, or something like this. So people at this same height we call 3. A married male would earn 7. Sorry, a single male would earn 7. A single female would earn 9. A married male would earn 10. And a married female would earn only 6, right? So let's look at what this interaction of the female and the married is telling us. That ceteris paribus, a married female compared to a single female, what happens? Well, when we go look at a single female, we're adding 2. But when we look at a married female, we have to do 2 things. Add in the 3 for married and subtract the 6, because they're a married and a female. And so if you take a single female and you add in the 3, 1, 2, 3, and then you subtract 6, you get back down to this orange line, predicting our value. Now, what I had in mind when I made up these dots are that many times married females, their job responsibilities or their family responsibilities are slightly different. When you get married, many times you'll start having children, and it's more often the females that will have the responsibility for raising the children, rather than having the responsibility to be the main income earner. And so this interaction term allows you to capture that. What if you left it out? What if you left out this interaction term? The fact that being a person who is married and a female normally takes a negative income hit. If we left out that interaction term, we would be forcing the coefficients for the other 3 to be wrong to try to absorb the data that we observe here. So what would happen? Well, if we took out the ability to really see what happened with married females, what would likely happen, I'm just trying to go through the math in my head here quickly as we talk. This married line, this line for married men, would, our estimate would be forced down, I think, because you would have two different types of people who are married in your data, males and females. And if what really happens when a male and a female gets married is that the man's income goes up but the female's income goes down, we wouldn't see that unless we had this extra coefficient. So what we would probably see is, when the regression was trying to explain what we're seeing, is that you have these single males, the green line, and you have the single females, the blue line. What would happen when people get married? It would probably, you wouldn't be able to capture the fact that the males' incomes go up and the females go down. So the estimated line you would get would lie probably somewhere in the middle here, right? You wouldn't be capturing the single males relationship or the married males relationship, or you wouldn't be also would not be capturing the married females relationship. Instead, you would get this mushy in between relationship that doesn't belong to anyone. And so what would happen is the coefficient for married would be biased downward, and you wouldn't be able to capture what's going on with these married females at all. So the danger of leaving out the interaction in this case is just like leaving out any important variable, you're going to have omitted variable bias creep into your regression. Now, in a similar way, you would want to test for different slopes between males, females, married males, and married females. I think it's more likely than not that one of those groups at least has a different slope than some of the others. And so you, in addition to having these dummy variables for female and married and interacting the female married, you would also want to have variables where you interact the female times the height, the married times the height, and even the female times married times the height, and that will allow your model to pick up different slopes for each of the four groups. So that was a good question, and I hope that this little example has helped you understand how interesting dummy variables and interacting dummy variables can be. And even though if you're just looking at a formula, trying to understand what these dummy variables mean can be difficult. If you take it step by step, it's not actually all that difficult. So thanks for that question.